Okay, thank you, Tyler. I'll try to be even shorter, probably, for the sake of time. But yeah, anyway, like, I mean, of course, thank you everyone for joining. Now we are at the time of closing and trying to wrap up this event. And like in general, what we talked about today was to put everything together, right? So having this sort of adaptation at large in different type of scenarios for different types of objectives. And we have seen a lot of different examples, right? Here I reported just something that Ricardo showed, and Tyler Zoll talked about the open world learning. And me and Ishwarya talked about the compositionality stuff or vision language or this type of different scenarios where you have a training set and you want to try to generalize to something. And either you do it while you are employing your model, like the examples that Ricardo and Tyler Zoll talked about, or you do it in an offline manner. And in that case, maybe you want to prepare your model for what comes next. And now we want to try to answer to the meme that Tyler put on the introduction. And so when to use maybe static versus dynamic type of approaches. I guess there are principles, but the answer is not that clear. So usually we employ static methods whenever we have data. I mean, if we don't have data that try to capture what we want to classify them at this time, the type of shift, for instance, etc., it's like just doesn't make too much sense to apply static methods. And so we are in a scenario like the one I described, where maybe you have different compositions, and then at this time you want to recognize something, like in this case, a dry dog, that belongs to what you have seen during training. So you add dogs, you add dry things and animals. This is something that you can recognize. But maybe you have to take into account that then you may have unknown objects and state at this time, or even or even unseen shifts completely because we didn't see any objects getting wet. And in this case, applying a static method actually may not really be working, because whatever you prepared during training doesn't then generalize at this time, just because the priors are different. What about dynamics method then? Well, dynamic methods instead tackle it from a different perspective, and you learn from the stream of data that you see at test time. So you are adapting while things are coming and you see them. And Ricardo made an example with the Oasis benchmark where you can really see things improving as you see data. And of course, even here, you need good priors, right? Like, because you don't minimize an objective that then deviates your model towards something that's not working. And Ricardo touched a bit upon that when talking about entropy minimization, for instance, that if you minimize something that can just shift the predictions of your model to a wrong stuff, maybe it's not the right objective. And also, of course, when on the open world learning, it's the same. In this case, we are most focusing on semantic, but even there, you assume that you can learn and detect things on the stream of data. Okay, pros and cons overall of the two. I guess we can draw a sort of line, and in the static part, what it's good is that you have a good initialization. So you are building a model that by design can generalize. And usually the inference is pretty fast, because you take your model and you apply it. Then there are cases maybe when the model is big or does weird stuff, but usually this is the case. The cons is that what we talked about before, that you need good data. So without good data, without data that represent the type of shift you want to model, you don't have any guarantee actually on the outcome of your adaptation process or preparation process. On the dynamic side, instead, of course, we didn't move, but we don't have we have no need of pre-collecting data. Of course, this is nice because we can just apply our model while deploying it, collecting data that represent your target scenario at least, or your target shift. And you have a flexible adaptation because as you receive data, you adapt your model to them. At the same time, though, this inference might be slower, especially if you have to adapt indeed as the stream of data arrives. And you may rely on primes, the ones that we were mentioning before. And of course, like even on novelty detection, you may have priors in the type of distribution that you are seeing, et cetera, et cetera. We will touch upon that later. In general, keep into account that you can apply both also together. You can use static methods to initialize your model, and then while the stream of data arrives, you improve the performance, its performance at test time. Okay, now just the last things are on open challenges, but I highlighted 3, but probably there are much more. The first one I think is on whenever we adapt on data streams, we assume something on the distribution that we receive. And one big assumption, for instance, is that the distribution of the data is IID. And this plot from actually a paper that tackled this particular scenario note presented like this big gap of a lot of models whenever you take them and you test in IID versus non-IID assumption. And this makes sense, right? Like it's similar to what Ricardo was saying, that if you adapt your model on semantic segmentation and autonomous driving, the sky and the road are present a lot. The car are present, but maybe you go out of an urban area and you see less bicycles or less pedestrians, and you don't want to model to forget. And here is similar. Like if you always see the same type of class, let's say your model can recognize cat, dogs, and horses. If you always see cats for a while and you do entropy minimization, your model will only predict cats and forgets everything else. And this is, a good thing to keep into account. And there is also the resource efficiency that Ricardo was talking about before. Another thing that also Zsolt mentioned is what we have as output space as target. This is like a work that tries to avoid that by having this vocabulary-free space where you don't actually assume that a human gave you the target labels, but rather you have a more unconstrained scenario where you take the labels by yourself. And the fact that humans have to specify things, it's a big limitation. Consider especially in open world learning, where when you detect an unseen concept and you say this is novel, you can perform generalized category discovery, etc. But the language tools that also Zsolt presented, they allow you to assign labels to things. And when you are able to assign labels and you can name things, then you can do other stuff, because maybe you named whatever you discovered as your new class, then you can download data from the web and perform incremental learning without having a human saying, oh, what you recognized a novel is, I don't know, an apple, and now I give you images of apples. That's not really practical. And the last thing is actually also taking into account multiple shifts. And so I talked before about composition, zero shot, and here things can go in different ways. Like if I am in this scenario and my model sees a tomato, of course it cannot classify it. It's a class that wasn't in the training set. But what about this? Like this is a dog, it wasn't in the training set, but it doesn't really correspond to the training distribution, right? And that means that my model will not know that it doesn't know this thing, and will probably misclassify it or just not recognize it anyway. And then there are also these weird cases, like this is both, like we have a new object and a new state, like Purid, that we didn't have during training. And how do we deal with these challenges when things mix, like where we want to perform novelty detection, incremental learning on multiple levels, for instance, like in compositional spaces? This is not trivial. And I reported also a citation from a paper of, actually taken from a paper of Attenberg that says that there are things that our model knows that it knows. There are also things that our model know that it doesn't know, and that maybe is for instance, the tomato that we've seen before. But there are also things that the model doesn't know that it doesn't know. And how to model that is very, very hard. And I guess you can find the inputs on the references that Tyler and Zsolt especially put out, but also on the book that came out on open word recognition. Okay, to wrap up, I would say that you have seen different ways in which we can approach this adaptation problem, statically, dynamically, of course. But the exact technique that you want to apply really depends on your actual application scenario. And I mean, you can check out our website if you want some pointers to that, or even reach us out. Okay, are there further questions? We are out of time anyway, but okay. Okay, I think there aren't questions, but I just wanted to say that, I mean, I thank you for, of course, joining our tutorial. I want to thank the other organizer, Aishwarya, Riccardo, Zolt, Tyler, and a special shout out to Tyler, actually, because it's really the mind and the ear behind this organization. So really thank you for all the effort. And I mean, if you don't have questions, just enjoy the rest of the conference, I would say. Thank you.